Hello, everyone. Come on in. Does anyone have any questions? Oops, muted myself for a second. Anybody have any questions while we wait for the rest of the people to enter? Any questions on last week's material or anything about the test or anything like that?
I have a question.
Yeah, go for
it. So I went to take the practice test for the third test, and when I opened it, there weren't any questions. It was just blank.
Yeah, I found out that was a problem. I think I've corrected it. Let me double check while I'm on here with you just to make sure, because I could be remembering the other class by accident, but that's not above me. So let me double check real quick. I just sent you guys an email. I created another one instead of just practice test 3, which covers chapter 5 and 6. I also created a practice midterm, and the practice midterm is actually 1 through 6. So it's more apropos to actually preparing for the midterm. Whereas this one, test 3, just covers 5 and 6. So if you need a lot more work on 5 and 6, but you feel pretty comfortable 1 through 4, you might want to focus most of your attention on that. But if you need some help with the previous stuff too, to be sure, then make sure you take the midterm. Yeah, this is working now. So yeah, I've fixed it since you did it, evidently.
Okay, cool. Thank you.
No problem. And I remember both of those count towards the extra credit practice test. Remember, I take every practice test that I post for you guys. If you don't take it by the day of the test, I put a 0 in there. But if you take it, then I just take your highest grade of all the times you take it, and I take the average of all those together, including zeros for ones you missed, and that divided by 20 is added to your final course score. So make sure you at least take the practice midterm once so you can get those points. Anybody else have any questions? Okay, we still got a little bit of time for everybody's supposed to be here. There's some more people coming in. I'm sporting my new hat that my coworker Leah Flax got us. Miss Flax, actually, the reverse nature of the universe here with this screen jacks me up. This side is clearly down, and I'm pointing to it right now, so I know it's this side, but it's on that side in my window, so it's way too complicated for me. All right, got more people coming in. I've already asked everybody if you have any questions. Now's a good time to ask them. Once everybody gets in, I'll re-announce my practice midterm thingy.
Just so you know, the practice test for the next in-person test is completely blank.
Is completely what?
It's blank. There's no questions on it.
Yeah, I was just addressing that with another student. Paige sent me an email on that I think it was Paige, sent me an email on that this weekend or yesterday, and I found it. So I fixed it this morning. So it should be ready to go. I just checked it a second ago, and it actually has questions in it now. What happens? When's the last time you tried it?
I think it was just before you changed it.
Okay, cool. Good deal. No, that's no problem. I appreciate y'all letting me know whenever that happens. I hope people do that initially, because it's kind of a weird thing when you take Canvas and you copy a test from another course. Sometimes it does perfectly. Other times it just randomly leaves the questions out. So I don't know. I haven't really figured out a rhyme or reason about why it does it. But anyways, it's very helpful when y'all do let me know. So, if you take it, especially when you first take it, when you first when I first release it, if you take it and let me know, that's awesome. It helps me a lot. But I usually check it. Just sometimes I get rushed and completely forget that step of you got to click in and you got to click in again and you say accept and then you look in here and you got to click on the individual banks to make sure they're working. So it's a little bit of a headache, but it's not so bad. Could be worse. I could have to actually type them by hand every time. Okay, so it looks like we've got 7 people in here plus me. That's not quite a quorum, so to speak, but it's good enough. So what because this will be posted, of course, what I wanted to let you guys know is, yes, there's a test 3, chapters 5 and 6, practice test that I posted. Definitely do that, and you should have at least 1 score on there. However, I also made a practice midterm, and that covers 1 through 6. I would say generally for everybody, I would take that test, practice test 3 once, or maybe good enough to get a score that you like, and then spend the rest of the time taking your practice midterm. Because remember, if you leave either one of those not done, that counts as a 0 in your extra credit column. And there's no reason to get a 0 in their extra credit column when you can get, at least a 25% or something by just guessing at all the answers. Because at the end of the semester, remember, I'm going to take all those grades and just average them together and divide that score by 20, and that's going to be added to your course grade. So I just want to make sure you guys take both of them. If you think you need the most help on 5 and 6 and 1 through 4 were a breeze, then spend most of your time on practice test 3. If you really just want to practice for the midterm and really have a feel for what you might encounter on the midterm, then you should spend all your time on the midterm practice midterm. So other than that, you should do both of them, of course, but just once you've done 1 each and got a score that you like, then by all means focus on what's more important or helpful to you. Our test will be, you guys meet on Mondays and Wednesdays, so it will be Monday. In your case, Mr. Mitchell will be having it during your lab. It'll be in Canvas, but it's a face-to-face test. So it's, even though it's online, so that you can get your score immediately, it's not an online test. You're not allowed to do Google searches. You're not allowed to have open notes. You're not allowed to have open book. All you're allowed is an equation sheet with the approved equations. And the approved equations are, of course, the ones that are numbered in your textbook. And any ones that I've given you and told you could use that even though it's not in your textbook or something, those are okay as well. And then you're also allowed some blank paper, the equation sheet, and a scientific calculator. And I don't mind if you use a graphing calculator, but we're not going to allow you to use Desmos or anything like that. You just have to use, and you can't use your phone as a scientific calculator. So make sure you actually have a scientific calculator. Hopefully everybody will kick butt and make a really high score and things will be good. Anybody have any questions before we get started on the chapter 7 material? We did some stuff in chapter 6, gravity, stuff of that sort. So anything? All right, well, remember the beginning of every class is really the time where you can get help on your homeworks. Ideally, what it would be is you run into a homework problem that was difficult for you. You take a screenshot of it. Maybe you email it to me and then I get back with you, or you just bring it to class with you and you share the screenshot. Excuse me. And you share the screenshot, and then we'll work through it. So that's what the first part of class is for every time. I often am really excited about starting class, so I might forget that and just jump right into covering class. That's when you tell me, "Hey, Mr. Younger, slow down. I need help." And that's fine. It won't bother me or anything like that. I would, I prefer you to do it because, obviously I'm goofing off and getting too excited about stuff. So anybody have any questions now that I've explained that again? We're up to 11 people in class. I'm feeling really good. Hopefully they'll check the beginning so they'll see what they missed about the midterm and the practice midterm and the practice test. But I guess we'll go ahead and get started on chapter 7. So in starting chapter 7, what I want to do is give you some motivation for the definition of work. So when we use terms like work or force or stuff like that in physics, we generally want that word work or force or whatever in physics to be closely related to what you know of it as in everyday life. Not all, and in fact, most of the terms that you use that happen to be in physics were borrowed from English, not borrowed from physics. So that's a big thing. So in this case, I'm going to try to motivate our idea of work with a very special way of looking at it. So I think you would all agree that mowing a lawn is work. And of course, when you mow a lawn, especially if you want to do it nicely and make it look nice, you might go from the northern border of the land, run east to west, back and forth, east to west, west to east, east to west, west to east, east to west, back. So what ultimately happens when you're cutting a lawn is basically you're walking the length of the lawn, and then the length of the lawn again, and then the length of the lawn again, and the length of the lawn again. And the number of times you have to do that is basically the width of the lawn divided by the width of your mower, something like that. So ultimately what you say is, well, the more trips I got to make back and forth, or the longer per trip that I got to go back and forth, you would consider that a more or a larger amount of work. So for instance, a yard that is 100 foot from the road to the back versus a yard that is 500 feet from the road to the back, obviously the 500-foot one is going to require a lot more work to mow that lawn. So that gives you the idea that work is directly proportional to distance. And that should make some sense. Yeah. The farther I've got to walk pushing that mower, the more work I'm doing. And for that reason, you start to see, well, if the two lots are the same width, but one's 500 foot deep and the other one's 100 foot deep, then clearly the 500 foot deep one's going to be 5 times as much, quote unquote, acreage. But again, the acreage is just a measure of the length of each path times the width of the lawn, which again, the width of the lawn divided by the width of the mower gives you the number of passes you got to make. So we now have, just from that idea of work, an idea that work is directly related to the distance you travel. Now, the other thing is, let's say you have a really new sleek lawnmower that is super lightweight. It's got big radius wheels, so it's easy to push, all sorts of good stuff like that. And it has the same horsepower as the other one, the same nice blades, the same sharp blades. So you don't have to do any extra cutting with that one when you do the other one. And then the other one's an older lawnmower that probably weighs, instead of 20 pounds like the first one, maybe it weighs 100 pounds. That clearly indicates that the 100-pound one's going to take more force to push it. So I think you would all agree that mowing with a 100-pound mower would take more work than mowing with a 20-pound mower. Therefore, you see work is directly related to force as well. So that's our sort of heuristic argument for what is work. Work is directly proportional to force, and work is directly proportional to distance. So let's see if we can work that out and see exactly what we want. So what I'm going to do is I'm going to share my screen. I'm going to use my iPad, of course. And now I'm sharing my screen, so it takes just a second. Okay, now you've got this. So what we just discovered was that work is directly proportional, and the symbol we use for proportional is this. So we found work is directly proportional to force, and it's directly proportional to distance. And that's actually turns out to be a pretty good idea, our first estimate of work. Now, in physics, we're going to clean that definition up, because what we want to do, like, is if I push a mower and I'm pushing down at some angle, then some of that force is being wasted. Some of that force as I'm pushing down is just pushing the actual lawnmower into the ground, and in fact making my friction force larger. So that component that's, you know, perpendicular to the direction I'm going is not that helpful. So you might say, well, work is proportional to F, excuse me, not that. I want to say F, nope, not that. F parallel times D. And what I mean by that is either you're going to take the component of D that's parallel to F, which is kind of weird, or you're going to take the component of F, which is parallel to D. And that seems to make a little more sense. Okay. So if you had, for instance, F like this, and you had, say, D like this as a vector, they're tail to tail, that would be the angle between them. Obviously, this component of force would be F perpendicular. but this component of force would be F parallel, and you could get that work is proportional to F times D times the cosine of the angle between them, because F times cosine theta is F parallel. Does that make sense to everyone? Well, it turns out in mathematics, there's a nice little neat operation that automatically picks components off that are parallel. And that's a fun thing to say, picks components off that are parallel. There's so many P's in there. It's called a dot product. So you might actually say, well, work, and by the way, we now know instead of constant proportionality, it turns out that because we're using force in units of newtons and we're using distance in units of meters, that it's actually exactly equal to F dot D, where a dot product, A dot B, is defined to be A times B times the cosine of the angle between them when they're tail to tail. Okay. So that is a definition of work. It's not quite perfect though, because what happens if the force changes along the distance D that you're doing? Well, then it gets a little more complicated, and you have to introduce the idea of work is equal to an integral of F dot DL, like that. Okay. And what's going on there is there's some path that you're following. At each point on that path, you have a little DL vector that way, and you have a force vector this way, and there's your angle theta. So you've got to break it up in infinitesimal little segments, DL, and they're got to be small enough where the force doesn't change appreciably, or you can easily calculate an average over that DL. And then you've got to integrate all of them from, whoa, I don't know how I just switched to eraser, but I did. Then you got to integrate all of them from X1, Y1, say, to X2, Y2. Okay. Now, if you just describe this DL in terms of X's, then it'll just go from X1 to X2. But you also might parameterize this curve by making it in terms of T, and then you go from T0 to T1 or T1 to T2, or if you make it in terms of Y, you might go from Y1 to Y2. So we can, we can sort of do it like this by just realizing that I'm going to put the point there and the point there, and just use the appropriate variables. Now, technically speaking, this is actually a line integral. And you haven't necessarily learned anything about line integrals because that's a Calc 3 topic, okay? It's basically vector calculus. But the good news is 99.9%, and I'm just making that number up. I just pulled it right out of my rear. But 99.9% of all the line integrals you'll do, doesn't matter that they're a line integral. You're probably going to integrate it properly anyways. But occasionally it will be a problem. So I'm telling you now that this is a line integral, and there's very specific rules about line integrals. When you're doing a line integral, you have to evaluate the integrand on the line or path that is followed. So like you might integrate along a path y equals x squared. That's okay. We can break that up into little differential area or differential length elements, dx, or maybe dy, and you have your function force as a function of y or a function of x. Well, what does that mean? That means that if your function f is a function, say, of x and y, and your path is, say, y equals x squared, then you could say, well, dy is equal to 2x dx. So what you do is you take everywhere you see a y and you replace that with x squared. And then you say work is equal to the integral of f of x, because we've gotten rid of y now, dotted with, or excuse me, yeah, because we've gotten rid of that, dotted with, since it's now in terms of x squared, we're going to say dx over 2x, something like that. Because I just divided this dy equals 2x dx, I divided that by 2x on both sides to get the dx instead of the dy. Okay, so that's one of the things. The other thing, though, is that you must show the direction of integration by exactly one method. So what do I mean by that? Okay. What I mean by that is if I want to integrate, let's say f of x is equal to kx. Okay. And I'm going to go from x equals 4.00 meters to x equals 1.00 meters. Okay. So then my work would equal the integral of kx I hat, because I'm assuming this obviously points in the x direction, right? If I wanted to make it a vector, I just put that there and put the I hat there. Now I have a dot product of, since I'm going in the x direction, but I'm actually going in the negative x direction, I can either say negative dx I hat, and that's me using dl to decide the direction. And then I go from small x to large x. Okay, in other words, the coordinate direction. So that's the case where I chose the dl telling you the direction. However, I could also say work is equal to the integral of kx I hat. And now I use the range of integration to tell me, in which case I go that I'd integrate it from 4.00 meters to 1.00 meters. And then I just have to use the positive coordinate direction, which is dx I hat. Okay, so that's what I mean. This one I'm using, well, this one I'm using range of integration to show direction. But in both cases, notice that the other one just has to point in the positive coordinate direction. Okay, that's the key. Again, you're probably not going to worry about this most of the time, but if you're ever up at night working a problem and you keep getting off by a sign, this is what you want to fall back on. So when I do actually compute this, notice in this case, I'm going to say I get, watch what happens here. The dot product is what we call a linear operation. So I can take the negative and put it out in front. I can put the kx dx, put it out in front, and then I just have I hat dot I hat. And you know from the formula, A dot B equals the magnitude of A times the magnitude of B times the cosine of the angle between them. You know that that's got to be just 1. Right? And of course, the integral of kx dx, negative kx dx, is just 1/2 kx squared. And I'm going to go from 1.00 to 4.00. Now, if I did this one this way, I would again get the integral of kx dx times I hat dot I hat, which again is just 1. But in this case, I'm going to go from 4.00 to 1.00. And of course, that's 1/2 K times, in this case, we're going to get 1 meter squared minus 16 meters squared, which obviously gives you negative 15 over 2 K times M squared. And M is just a unit, so that's why I just wrote it out there in parentheses, which is exactly the same thing that you got here, because you get 1/2 KX squared, and it'd be negative of 16 minus 1. So that's also going to be negative 15 over 2 K meters squared. So that's the weird thing about line integrals. It's not that big a deal. Most of the time, it's not going to be a problem, but I just wanted to tell you up front, when you're doing a line integral, you've got to evaluate the function, which luckily in this case, it was just f equals kx. So the x was there, and all I had to do was go along the x-axis. So that's really, by having a kx and a dx in there, I've already shown that I'm going along the x-axis. If I was doing something more complex, like along y equals x squared, then I'd have to convert the y to a parameterization with x or something weird like that. So that's, way more complicated than you need it. And the good news is you're not going to do it very much at all this semester, but next semester you will. So I'm just giving you a little bit of a heads up. So
I had a quick question. Sorry, just
Yes.
for my own understanding. In the first example, we're just basically switching out the bounds so that we don't have to include the negative on the inside.
Sort of. Okay. So when I say a line integral or a path integral, what I mean is I'm actually carrying out integration over a distance over which something's traveling. In this case, it could have been a mass attached to a spring, and that would actually give us the force kx, and it's traveling along the x-axis. But it traveled very specifically from the x equals 4 meters to the x equal 1.00 meters. So I either need to indicate which direction it's going by putting a negative sign on the dx I hat, or by putting the range of integration from 4 to 1. If I did both, they would cancel each other out, right? And you end up getting
That makes
off
sense.
by a sign.
I see. Yeah.
That's why that's the only thing we're doing. So the other one automatically just becomes the default positive coordinate direction. So you choose either the DL or the range of integration to tell you which way you're going. And the other one's just the default positive coordinate direction. Okay.
Right. Makes sense. Thank you.
No problem. And again, like I said, I'm being pedantic by showing you this much right now. You could force yourself to make sure you do it with some of the problems we have in our homework, but generally speaking, you're not going to need to at all. So what I'm going to do now is I'm going to look at a very specific example of work done. So let's imagine that we have a block, and the block, let's say, has a mass of 10.0 kilograms. And let's say it's on a surface that provides a friction force F is equal to 50.0 newtons. And I'm applying a force downward, if you will, of 100.0 newtons at about 37 degrees. Okay. I am going to push this thing a distance of D equals 40 meters. Okay. And what I'd like to know is, what is the work done by F? What is the work done by the friction force? What is the work done by the normal force? And what is the work done by gravity? Okay. So we know work is equal to the integral of F dot dl, But in this case, we actually have a constant force. Implies no integrals needed. We're just going to do F dot D. Okay. Notice I didn't even call it a DL anymore because I'm going a whole distance or whatever. No big deal. So first off, I'm going to draw a free body diagram. And I'll say this is my x-axis. And this is my y-axis. Okay. Now in this, I will have, say, a force this way. Which is the normal force. I will have a force this way, which is mg. I will have a force. Whoa, no, did not mean to do that. Stop. This way, which is the friction force. And I have this odd force that isn't really along either coordinate system. So I'm just going to color that green and say this angle is 37 degrees. Okay. So this mg, by the way, is equal to 98.0 newtons. This F is equal to 50.0 newtons. This normal force we don't know yet, but what we can do is we can realize that the y component of this force is downward. And the x component of that force is to the right, which is a positive direction. And that's a negative direction. And we can see, since this one, this green force happens to be a force of 100.0 newtons, which, by the way, 100 is actually 20 times 5, and this looks like the 3, 4, 5 triangle. So I can immediately say that, for instance, this guy right here is the small one, so that must be 3 times 20, or 60 newtons. And this guy right here is 4 times 20, so that must be 80 newtons. And that's really 80.0 and 60.0. But that's just from knowing that basically the cosine of 37 is pretty close to 4/5, and the sine of 37 is pretty close to 3/5. Okay. So now I can say the summation forces in the y direction equals mass times acceleration in the y direction, which is 0, right? It's not going to be bouncing up and down. That gives me that F normal minus 98.0 newtons minus 60.0 newtons is equal to 0. So that gives me that the normal force is equal to 98 plus 60 would be 158, I think. 148 newtons. Hopefully my math works out there. You know how I am with arithmetic. So now the summation forces in the x direction equals mass times acceleration in the x direction. Now in this case, I'm going to plead something here with you, okay? I am going to apply just the right force as it says here, but I'm not really going to assume that it's accelerating the object at all necessarily, okay? Well, I'm not going to worry about what the acceleration is. Let's put it that way, okay? So I don't really have to do this part. I know all the forces acting on it, so I can just use those. So now I'm going to say the work done. Let's change it to a different color. Let's say the work done by F. Well, F is actually 100 newtons times the distance, which is 40.0 meters, times the cosine of the angle between them when they're tail to tail. So you can see the displacement vector D is like that, and the force vector is like that. And you see that when they're tail to tail, that 37 degrees is the actual angle. So I'm going to say cosine 37 degrees.
Professor,
Yes.
sorry to interrupt, but
No
the normal force is actually 158, and Sarah caught that.
Oh, thank you. I was hoping somebody would catch me on that or check me on that. Thank you. Yeah, I should have known that. It was 98, not 88. So anyways, so 158. Thank you. Okay, now what I want you to see here is a very important result. Notice when you multiply cosine 37 times 100 newtons, you're going to actually just get the 80 newtons that I'd put up here in the diagram. So that's actually going to be 80.0 newtons times 40.0 meters. And that actually gives us our figure, which is 3,200. But it gives us our unit too, which is called a joule. So 1 joule is defined to be 1 Newton times a meter. That's our unit of energy that we're going to use. It happens to be right now just a unit of work that we're going to use, but it's actually a unit of energy, as you'll see shortly. And to give you some idea how big it is, it's about as much energy as required to take a red delicious apple and lift it off the ground and stick it on a tabletop. So lifting a red delicious apple about a distance of a meter, a little bit less than a meter maybe, that's about 1 joule of work. Okay. So notice that in fact worked out to be, I'm going to write it in green so you'll see what I'm talking about. This actually turned out to be the component of F parallel to D times D. Okay, so that's sort of the learning part that I want you to see. The dot product in a line integral or in the formula for work in general is really just choosing the component of the force that's parallel to the displacement or the component of the displacement that's parallel to the force. So now I've done one of the works. I did the work done by friction, or excuse me, the work done by my force that I was pushing it with. Now I want to do the work done by friction. So the work done by friction, I don't know why I chose to do green. I know I did over there for a reason, but I was supposed to change it back, but here we are. So, whoa, and something crazy just happened. Okay. So the work done by friction is going to be the friction force, which is 50.0 newtons, times the distance, which is 40.0 meters. Now, if you look, the angle between the friction force, which is this way, and the displacement, which is this way, you see the angle is 180 degrees. So it would be cosine 180 degrees. So in this case, you're actually getting 50 times 40, which would be 2,000 joules, but it's going to be negative because the cosine of 180 is -1. The work done by the normal force is going to be the normal force, which luckily you calculated for me correctly. Whoa, I have no idea why it keeps changing like this, but anyways, it does. 158.0 newtons times 40.0 meters. Now, in this case, it's times the cosine of 90 degrees. I think you can see that the normal force and the displacement make a 90-degree angle, as I just drew there. So cosine of 90 gives you 0, so we get 0 joules for that one. I think you can tell also that the work done by gravity is also going to give us 0 joules.
I have a question.
Yes.
So why, when we're calculating for the friction, the work of friction, we have to do 180 because it's going in the opposite direction of where like its displacement is?
Right. So
Okay.
Go ahead.
So it all depends on like where, well, never mind. Friction's always going to go against the motion. So we can
In some
always
sense,
assume.
yes.
Okay, all right. I don't know, that tripped me up for a second.
Yeah, actually what we're doing is ultimately what we're going to figure out is the work done can be equal to the change in potential energy. So if you put a positive amount of work into something, like I grab a 10-kilogram box sitting on the desk and I slowly lift it up. And by slowly, I mean so slowly that my force is just 98.0 newtons. It's 0.0000, maybe about the 480th decimal place, there's a 1 in there or something. So it's just going a little bit better than 0, but it's not really accelerating it appreciably. So it's going to take forever for me to lift it from the desktop to the ceiling. Okay. When I do that, then I'm just applying the work to lift it up. And now, as a result of that box being up, say at the height of the ceiling, it has the ability to do work by falling back down on something and say driving a nail. So if we want that idea where the amount of work in goes into the changing of the potential energy, then we need a negative of work as well, where you're actually taking away some of the potential energy. And that's what friction has done here. The friction has fought against the block by a force directing in the opposite direction. And because of that, some of the potential energy we could have gained, or some of the energy we could have gained, has now been lost. So instead of getting the full 3,200 that we put in, we're going to get the 3,200 minus 2,000. So we're really going to get only what, 1,200 joules. So that's why that negative comes in. And anytime you have to have a bare minimum of a component that's parallel to the displacement. If you don't have any component whatsoever parallel to the displacement or anti-parallel, then the work is going to be 0. If the component is somewhat parallel, then it's going to be a positive quantity. If the component is anti-parallel, it's going to be negative. Okay, does that help?
Yeah, it does, because I remember talking about conservation of energy, and it makes more sense that way.
Yeah, that's where we're going. Is
Yeah.
this is a whole different paradigm. We've been learning about Newton's laws of motion, where we had to use F equals ma, which, by the way, Newton didn't have any idea of vectors. He was using them in some sense, but didn't know it because vectors weren't invented yet.
Good
But
for
all
him.
of Newton's equations are, yeah, exactly.
Good for them.
That's why his book was so long, because he had to explain everything in terms of magnitude and direction, and just didn't come up with a succinct language. But what we do now is, by getting away from F equals ma, we can stop using vectors somewhat and do the same problems, but using it in scalar.
Energy.
Yeah,
Oh,
that's what work and energy is. It's about scalar quantities.
Yeah. Okay, thank you.
No problem. Now you can look, there's a similar problem to this one in the book, but they did it where the force was actually applied in an upwards direction. In fact, I've been looking at it now. Oh, they even used the same, they used the same parameters. So they said upward at 37 degrees. They still use 40 meters for the distance, and they still use 50 newtons for the friction force. So I guess I just happened to have chosen the exact same numbers they did. But either way, that's another example for you to get some feel for. Now what I'm going to do is one that is also, this one I intend to be like the one in your textbook, and it's the work done in by a hiker carrying a backpack. So let's imagine that a hiker is carrying a backpack, Okay. He's obviously got one leg shorter than the other. I don't know what happened there. This is a terrible accident. We're all praying for him and his well-being. But anyways, the mass is going to be, let's say 50.0 kilograms is what I'm going to make it. And let's say he's going to walk up this incline. And in fact, he's going to walk up a distance D that we really don't know. In fact, all we're really going to know is that he's going to change his height H by a distance of 20.0 meters. Okay, so the box or the backpack is going to stay the same height relative to him. So it's going to start a couple feet higher than 0, but it's going to finish a couple feet higher than 20 meters as well. So what we want to do is calculate the work done by basically all the forces in some sense. So I'm going to draw a free body diagram again. Let's draw a free body diagram in green. I'm going to say that's my x-axis is horizontal and my y-axis is vertical. And I'm going to have a mass M right here. And then acting on it is, get this, we're gonna do sort of what I was talking about when I lifted that block earlier. Unlike what we did when we slid the box along the flat table. In that one, we actually had a net work of 1200 joules. And in fact, when we learn about the work energy theorem, you'll know where that energy went. But in this one, we're going to assume that I'm going to move so slowly horizontally or diagonally up, either way you want to take it. We're going to move so slowly that the backpack doesn't really accelerate. It just stays a constant speed. In other words, I'm just going to apply, as the hiker, if I am the hiker, I'm going to apply just the bare minimum of force needed to lift it up a little bit higher, lift it up a little bit higher, lift it up a little bit higher, and move it to the right a little bit more, move it to the right a little bit more. In other words, it's never going to speed up. Okay, so there's no acceleration going on is really what we're doing with this one. And that's, I started to lead off with that block, but that I was doing sliding across the floor, but I chose to change my mind on that at the last second because I figured that would bring in a complication too early. So that's why I started off saying that. Now we're doing one where I'm actually going to use this. So what forces I have acting on it are going to be basically an upward force that I'll call the force due to the hiker, F sub H. And then there's going to be a negative force that's going to be mg. Okay. And I think mg should be 490 newtons, 9.8 times 50. So that's the force downward. And therefore, since the summation of the forces in the y direction equals mass times acceleration in the y direction, and I'm making that 0, that means FH is going to be equal in magnitude to 490 newtons because it's FH minus mg is equal to 0. So that gives you that. Similarly, the summation of the forces in the x direction equals mass times acceleration in the x direction. Again, I'm saying the force is just enough to make it move, but not enough to make it accelerate. So this one doesn't give us anything. In fact, we're not going to have any horizontal forces. Okay. You can sort of pretend maybe the hiker had just started rolling on a unicycle, say, with a free will mechanism and was rolling towards the incline and just continued to go up. That's one way of thinking about it, because then it's just in uniform, quote unquote, uniform motion. Okay. Now that we have that, we can calculate the work done by the hiker. In this case, the force is not going to change. So we're again just using work equals F dot D. So the magnitude of the force of H is 490 newtons. the distance traveled will be d, which we don't know, okay? But what we can see is that from the diagram here, I have a inclined plane, and in fact, the angle between this force and this force is the one we want to know. I'm going to call that theta. This force and that displacement vector d. Okay, so this little guy right here is d vector. So I'm going to have to say times the cosine of theta. But if we look close at this diagram, we can see this is h, or lowercase h, excuse me. This is lowercase h. This is theta, which means, notice this line and this line are parallel. They're both vertical. This is a bisector. And this theta is an interior angle. And this angle right here is on the alternate side. So those two are actually equal to each other. Okay. So the reason why I say that is you can see that d cosine theta, which is what we have here, is just equal to h. So we get 490.0 newtons times h, which is 20.0 meters. And that gives me 980 or 9,800 joules. So the usefulness of this example was for you to see they didn't give us D, and we thought we were going to need it, but in fact we didn't need it because it turned out that the dot product that we use for our formula for work gave us D cosine theta, but D cosine theta happened to be the height. And of course, the actual climber or the hiker is applying a force in the vertical direction. And the only component of D that's parallel to that is H. So that's why it turned out to just be H times F. Now, if you look at the work done by gravity, notice gravity points down. So in fact, this angle is 180 minus theta. Everybody sees that? So what we do in this case is we say 490 newtons times D. Let me back up a little bit there. Times D. Now I'm going to say times the cosine of 180 degrees minus theta. But if you look up, and this is on the last page of your textbook, there's a trig identity that says cosine of 180 minus theta is the same thing as negative cosine of theta. So I'm going to get negative 490 newtons times D cosine theta. And of course, D cosine theta, we already discovered was H. So in fact, I'm going to get a work of negative, that just turned out terrible. I'm going to get a work of negative 9,800 joules is the work done by gravity. So the difference here, notice, is the total work is equal to 0. Okay. That's because the hiker put in 9,800 joules of work, gravity put in negative 9,800 joules of work, and the net amount of work was 0. And there's something called the work energy theorem that says the net work done on any object is equal to its change in kinetic energy. We're going to derive that in a second. So I was telling you very precisely that this box was, or this hiking backpack was being moved ever so slowly so that we didn't actually accelerate it. It's just going to start at the bottom and end at the bottom with no speed, right? So in this case, the change in speed, which is what kinetic energy measures, is how much the speed squared times the mass times 1/2, how much that changes. It hasn't changed at all. That's why the total work done was 0. Whereas in the previous problem, when we did this, we found the total work was 1200. So work total equals 1200 joules. That work would in fact be a result of this thing accelerating, because I'm putting a force bigger than the force of friction. I'm putting in 100 newtons. The friction force is 50 newtons. So the remainder of that force, which is another 50 newtons, or actually it's 80 minus 50, because we got to take the component parallel. So 80 minus 50 would be 30. That 30 newtons is going to be equal to mass times acceleration. So 30 is the force, the mass is 10, and the acceleration is a. If I divide 30 equals 10 times a by 10, I get 3 meters per second is equal to a. So this thing is going to actually accelerate at a equal 3.0 meters per second every second. So because it's accelerating, it's actually going to start off, say, with initial velocity v initial equal to 0, but at the end it's going to have some final velocity, which we can calculate. Does anybody know what kinematic equation we might want to use to find the final velocity given the acceleration and the initial velocity and the distance traveled? Anyone?
I think you might be cutting out a bit because the storm is hitting a lot of us. And
Oh, okay.
like, yeah,
Gotcha.
right now I can barely hear you. It's like,
Well, that stinks. Crap. Okay. So what I was doing was reflecting on the difference between this problem, where I worked really hard to give you a scenario where the hiker was moving this box or this backpack with just enough force to move it, but not enough to really speed it up. So that at the end, the backpack was at the top of the hill, but at the beginning and the end, the backpack had 0 speed. And in fact, we ended up getting the total work was 0, as shown in the bottom of this page. Well, what I'm saying is there's something called the work energy theorem that says the total work done on a system is equal to its change in kinetic energy. So this had a total work of 0, which is exactly what you'd expect, since the speed before and the speed after were both 0. The change was 0. In this case, what I'm arguing is that this one actually had an acceleration. We can calculate it, because what we knew happened was this 80 newtons right here was applied to a 10 kilogram mass with a 50 Newton friction force fighting it. So we end up getting 80 minus 50 is equal to 10 kilograms times A. So 80 newtons minus 50 newtons is equal to 10 kilograms times A. That's Newton's second law. So we get 30 newtons is equal to 10 kilograms times A. That gives us A equals 3 meters per second per second. So we could actually calculate what that final speed would be, and we could do it using a very specific equation. So let's go back and think for a second here. We know that V initial is equal to 0. We know that V final is equal to what I want to know. And we know that the acceleration is equal to 3.00, say, meters per second every second. And we also know that x minus x0 is equal to 40.0 meters for that problem. So can anybody think of what kinematic equation we want to know to use to find V final?
is this the V final squared equals V initial squared?
Absolutely.
Okay.
Remember, it's 2a x minus x0, which we can almost always say x0 is 0, but I decided to call x minus x0 just 4 meters, 40 meters. So that works. So now we'll say v final is equal to the square root of 0 squared plus 2 times 3.0 meters per second every second times 40.0 meters. So we can say 6 times 40 is in fact 6 times 4 is 24. That's 240. So it's the square root of 240 meters squared per second squared. That is not all that helpful until I use the square root. So I'm going to say, if I can get my calculator to come on, square root of 240. Oh, my calculator's dead. So I'll be using my calculator on my phone, I guess. That's nice. That's helpful. Okay, hold on a second, everybody. All right, I'm going to say 240. And now I'm going to take the square root of that. And I get 15.49. Meters per second. So technically you'd have to choose whether positive or negative, but obviously that's not relevant here. So that's something kind of neat. That gave us the final velocity. Now you haven't learned yet about this quantity that Madame de Chatelet called oomph, okay? But it's something called kinetic energy. So let me take the screen back for just a second and stop sharing. So Madame de Chatelet was this brilliant young lady who married at a young age, as everybody did back then. But by the bright old age of 16, she had already translated Newton's Principia from Latin to French. Brilliant woman, literally so brilliant that, you know, Voltaire was probably 10 years her senior, and that was sort of like a quote unquote boy toy for her. Voltaire, as brilliant as he is, this young lady, you know, led him around like a little puppy dog or whatever. But Voltaire was super, super smart. And that tells you, obviously, this woman was very, very intelligent. And she did, like I said, translate the Principia from Latin to French. But she also came up with this quantity that she called oomph, O-O-M-P-H-F, or something like that, which is really just kinetic energy, okay? She was a bright physicist by her own right. She was married to some kind of nobility. She ended up dying. I think she was maybe 30 something, died in childbirth. Really tragic story, but she was awesome. And everybody should know her just because of how awesome she was at such a young age even. So I mentioned that to you just because women get a lot of short shrift when it comes to sciences. So I always try to mention all the foundational women when we run across them in astronomy, physics, chemistry, biology, any of those kind of things. So Madame de Chatelet is definitely one I'd recommend you look up. Now, from that, what I'm going to do is I'm going to introduce a quantity called kinetic energy, but I'm also going to introduce another quantity called potential energy. And what it is I like to think of work as the ability to drive a nail. So if you do work, you've done the equivalent of driving a nail. What do I mean by that? Well, I mean, imagine a scenario where you got to drive a nail. Now, the nail can be infinitely sharp. That's perfectly fine. The diameter can be infinitesimally small. So any itty bitty force could be considered, but you got to drive the nail. So you can't just hit it and it moves a little ways. You got to actually be able to drive it. So you got to apply that force over a distance. And that nail doesn't have to be driven into hardened steel. It can be driven into soft steel, or it can be driven into a marshmallow, or into styrofoam. Anything or any action that would allow a nail like that to be driven like that into something is something that is work, because it requires force applied over a distance where some component of the force must be parallel to the distance. That's it, right? With that in mind, then you can say potential energy, which is an energy related to an object's location. Potential energy is an object's ability to potentially do work. So if you take, fat Mr. Younger and you put him up on top of a telephone pole, and you put down at the bottom of the telephone pole, just a few feet away from the bottom of it, one of those big gutter nails. Gutters on your house are hanged often with long aluminum nails that are about that big in diameter and got a huge head, and they nail through, because the gutter's like shaped like this or whatever, they nail through that distance, and there's this little metal thing that keeps the gutter from compressing that way, and then into the wood, so it's actually got to be quite long. So you imagine sticking those, just getting it started in the ground at the base of the telephone pole. I then fall off of the telephone pole, and landing on the nail would obviously drive it. So you can say, oh, okay, so because Mr. Younger was at a height, he had the potential to do work, therefore he had potential energy. And that work turns out to be, or that work, as you can tell, would turn out to be the minimum force required to move it, which would be mg, times the distance that it travels upward, which would be h. And those two are parallel to each other if you're really minimizing it. So mgh is your potential energy. Now, if you look a little closer at that, you might say, well, wait a second, Mr. Younger. If mgh is the potential energy, as soon as you fall, your potential energy is dropping, because your H is going down. And I would say, that's awesome. Yeah, that's exactly what happened. So I've got to account for another form of energy. In fact, just before I hit the ground, my potential energy was very, very close to zero. But I still had as much energy as I did when I left the pole, assuming air resistance is negligible. So it turns out there has to be another form of energy, and that energy is the energy of motion, which we call kinetic energy. Okay, so what you'd see is as my potential energy was dropping, this thing called kinetic energy was going up just the same rate, so that when I got to ground height, my kinetic energy was now exactly equal in magnitude as my potential energy at the top of the pole. And now that kinetic energy, also being a form of energy, has the ability to do work and therefore could drive the nail. Okay. So now I'm going to introduce you to this quantity, and I'm going to do it by the work energy theorem. Okay. I've already sort of highlighted what we did with the potential energy, gravitational potential energy, and there's other types of potential energy. The potential energy is generally an energy of position. So you can think of it as the energy due to gravity and your height above some location that you're calling the zero potential energy. So from the surface of the earth up to however high you are might be one. But if you're living in a second or third story of an apartment building, and you never leave that third story, then maybe it's not useful for you to talk about the energy being zero at the surface of the earth. Maybe it's useful for you to talk about the energy being zero at the third floor. And you're still going to get all the right answers, because it turns out that you can add any constant amount of potential energy to any energy, and all that really matters is a change in potential energy. So you can call the zero of potential energy anywhere you want. Long as you stick with that, all your problems will work out fine. So that's the energy of position. Now, you can also be energy of position because I've hung this mass from a spring, and now it's stretched the spring. Well, it's got some potential energy due to gravity, but if the spring were sideways, it's also got potential energy due to it stretching the spring. So that's another type of potential energy. Or you can say, how far is an electron from the nucleus of an atom? Well, that's an electric potential energy. So there's all sorts of types of potential energy. We're dealing with gravity right now. And as you saw with Kx being the force, we're going to deal with the spring as well. So let me go back to sharing my screen. And I'm probably going to need to turn this on, evidently. Okay, so we had that calculation before, and that doesn't have anything to do with us right now, but I'm going to use it in a minute. That's why I started with it. So first off, I'm going to picture an object of mass m having a weight mg. Okay, the bare minimum force that I can put on it to lift it is equal to mg. Does that make sense? If I give it any more force, it's going to actually accelerate. And again, I'm trying to lift it ever so slowly so that it takes 100 years for me to lift it to a height h. Okay. So in that case, the work is still F dot D because the force isn't changing. It's just mg. So that's going to be m times g times the height h that I'm going to lift it. So I'm going to take it from here and go all the way up here to a height h. And in fact, the mg and the h are parallel. So the cosine is just the cosine of 0 degrees. So I get work done in lifting it from h equals 0 to h equals h is just mgh. And I call that my potential energy. This is the symbol we use for it. Sometimes people will use this one. Sometimes people will use this one. Okay. Your book is mostly sticking with U and occasionally PE, but I'm going to say it's MGH, and the 0 can be anywhere you want it to be. You just have to be consistent throughout the problem. Okay. So what that means is a change in potential. Remember, we just decided when we were doing kinematics that the delta could mean change in, and it's always final minus initial. So that would be the change in potential energy is U final minus U initial, which would be mgh final minus mgh initial. So that's another way we can look at it. These are all important equations that we can use. Okay. Now that was one of them. That was the potential energy. There also happens to be something where we can imagine not just working with Newton's second law, the summation of the forces is equal to mass times acceleration. That's Newton's second law, right? And this part right here is the net force. So the net work, which might also be called the total work done, would be equal to the integral of the summation of the forces dot dl. Does that make some sense to you guys? In other words, if you add up all the forces acting on an object and dot it with the little incremental dl vector for each little part of the path it's going in, and then summation, take a sum of all those via the integral, you'll get the total work done. So W net is equal to the integral of the summation of the forces dotted with dl. Well, if I start with Newton's second law of motion, I can say the summation of forces dotted with dl is equal to m, but instead of a, I'm going to call that dv dt. And since I dotted it with dl on the left, I got to dot it with dl on the right. Right? Or I'll make the equation no longer valid. So now I can try to reassume or reorder things. I'm going to take that dt, and instead of associating it with dv, I'm going to associate it with dl. So I'm going to say the summation of the forces dotted with dl is equal to m dl dt dotted with dv. What does dl dt look like to you guys? Even if you just have to look at units, that'd be fine.
Velocity.
Yes, it has units of meters per second. In fact, it's a length per time. So yeah, it is truly a velocity. So now I'm going to integrate both sides, and I get W net is equal to the integral of mv dot dv, which equals 1/2 m v squared from v initial to v final. So what that means is the total work done, or the net work done, is equal to 1/2 mv final squared minus 1 half mv initial squared, which is the same thing as the change in kinetic energy. Okay. Now, that also is sometimes used as just K, so delta K, or it's also used sometimes as delta T for whatever reason. But the main thing is kinetic energy is defined to be 1/2 mv squared. Okay. And that tells you something neat. It tells you, for one thing, I know right now my students are sitting right in front of their computer, not running around or anything like that. They have zero velocity, they're just sitting there. And I know the last time I saw you guys, y'all were doing the same thing. Well, that means your change in kinetic energy from then until now has been 0. So the total work done on you since the last time I saw you is in fact 0. That is the work energy theorem. Whoa. And it basically says W net is equal to the change in kinetic energy. So we can now test that. Remember, we were doing this problem a second ago where we found that the object was going to speed up from 0 meters per second to 15.49 meters per second. Well, the object happened to be a 10 kilogram mass, right? And we found that the total work done was 1,200 joules, assuming my 3,200 minus 2,000 was right, which I think is right. So now I can say, in that one case that we did, work total, which is work net, was 1,200 joules. The change in kinetic energy, though, which is 1/2 mv final squared plus, or excuse me, minus 1/2 mv initial squared. I'm really having problems writing letters today. I don't know what's going on. Okay, well, that part's just 0. So I'm going to get 1/2 10.0 kilograms times 15.49 meters per second squared. Well, we know what 15.49 was. That was the square root of 240, right? So that's 1/2 times 10.0 kilograms times 240 meters squared per second squared. And in fact, if I take 10 and multiply that by that, then I'd get 2,400. Notice the units are kilogram meter per second squared times a meter. This is in fact a Newton. Therefore, what we have here is a joule. And of course, 1/2 of 2,400 is 1,200 joules. So our other problem, that very first one we did, is completely consistent with the work energy theorem. Does that make sense to everyone? All right. So we've introduced a few new equations. We've got work in its most general form as the integral of F dot dl, okay, which is a path or line integral. Which has rules associated with it. Like I told you, you've got to use either the DL or the range of integration to tell us which direction you're going. And the other one just has to go in the positive coordinate direction. And you need to actually evaluate the entire integrand along the path by substituting, for instance, an equation for the path or something like that in there to eliminate one variable. We've also came up with a concept of potential energy, which is equal to mgh. And we've come up with a concept of kinetic energy, which is equal to 1/2 mv squared. And we found the work energy theorem, which says that the net work done on any system is equal to the change in kinetic energy. So that's what we've done so far. Now, if we want to talk about a particular instant where a force is not constant, so for work, or let's not say it that way, work done when a force is not a constant. So a good example of that is Hooke's law. Which says basically this, that if you apply force F to say a 2x4, maybe you've got a 2x4, it's locked in a vise and you're grabbing one end and you're pulling it. The vise is held down, it's not going to be able to move. What you will find is the 2x4 is going to apply a force to you that's in the opposite direction you pull it, so that it's going to be a negative, and that force is going to be proportional to the distance that you stretch the 2x4. The constant of proportionality is a constant of the material. Now, for instance, if you did it with a southern yellow pine 2x4, you would get a different K value than if you did it with a spruce pine fir 2x4, which is really just they take a mixture of spruces and pines and firs, but not necessarily southern yellow pine. And they're all so close that they're pretty much the same thing. Or in a really simple way, you can think of it as forget about stretching 2x4s. If we actually apply a spring, in other words, apply the force to a spring, we'll get a constant called the spring constant. So in that case, it's just called the spring constant, and it's something you can determine for a given spring as long as you don't stretch the spring too far. Like all of you've probably had a slinky before, and if you stretch a slinky too far with one particular loop, then it's going to get a spring in it in such a way that the slinky never sits flat anymore. It's got that lump in the middle. Okay, you've exceeded its elasticity at that point, and therefore the equation doesn't hold quite as well. But the main thing is to realize that this negative is just telling you that the force that the spring or the 2x4 is applying to you is in the opposite direction of the force that you're applying to it. Okay? So this is a case where the force is not a constant. And we might, in fact, imagine for a second a spring and let's say we give this a pull with a force F, and I'm going to move it from x0, where the force was 0, in other words, its equilibrium position, to x1. Now, the force I have to apply, F, has got to be equal in magnitude to the force that the spring's going to apply. If I give it any more, it's going to speed it up as well, but I'm going to try to do that balancing game that we've been talking about the whole time. So I'm going to say work done by me. So I'll say work by me is equal to the integral of kx, and that's going to be pointing in the I hat direction because I'm actually pulling it. This is my x-axis. This would be my y-axis, say. Now, it's a line integral, so I'm going to choose the dl to indicate my direction, and I'm going to do that by saying plus dx I hat. Now, by default, that means the range of integration has to go from low to high, so it's just going to go from x0 to x1. So what happens there is, again, the dot product is what we call a linear operator. So that means all the little giblets out in front of the I hat that's actually doing the dot product, and the other I hat, which is actually doing the dot product, all those can just come out in front. So I'm going to say the integral of kx dx I hat dot I hat, which we know is just 1, from x0 to x1. K is technically a constant, so I could pull that out if necessary, but it's not really a big deal. I'm just going to say it's equal to 1/2 k x1 squared minus x0 squared. So now we have a neat new formula. Work is equal to change in potential energy of a spring. In that case, we say potential energy of a spring. Actually, let me do it this way. I'll say U spring is equal to 1/2 k x squared, where this is the amount of stretch. And I mean amount of stretch from equilibrium. Okay. So we now have a whole new equation that we can use. And that's another form of energy, if you will, that we can think about when we think about, say, cocking a little toy gun or something like that. If the gun has a spring mechanism in it that makes it a quote unquote toy gun, then you can imagine pushing the spring in until some little lever catches it and holds the spring in place. Then you've managed to do a certain amount of work on it equal to 1/2 kx squared, where x is the distance from where the let's say the dart or the ball that you're going to shoot was at equilibrium to however far you pushed it in, x. So now we have that. Any questions on that? All right. No questions on that. I want to tell you about dot products, which we've already covered them to some extent, but I'm going to show you what I think is important about dot products, or at least what I think helps me. Is one thing, we use dot products in physics a lot, and dot products are used for picking off parallel components. Dot products. Whoa, Nelly. I don't know what just happened there. Let's see if I can do a back thing. Yes, I can. Okay. So dot products. They pick off parallel components. Like if you're wanting to figure out how fast your boat's making it across a stream, the stream's like running this way and you're going that way. What you want is the component of velocity that's parallel to, say, north-south. If the stream is running east-west, you want the component of velocity parallel to it. So you take a dot product of the velocity with a due north vector, and you'd actually get a velocity component that's parallel to north. So that's what we use it for. And the reason why should be somewhat clear, but just in case, I'm going to remind you that one definition of A dot B is equal to the magnitude of A times the magnitude of B times the cosine of the angle between them. And what that literally means is if this is A and this is B, notice they're tail to tail, then that's the angle theta. Now check this out. I can draw that way, and that's perpendicular. You see that this part right here, this blue line that I just drew, is the component of A that's perpendicular to B. So I might write it A perpendicular to B. And this component right here is the component of A parallel to B. But I think you can see that that is actually just equal to A cosine theta. So you're going to get B times A cosine theta, which is just B times A parallel. That makes sense to everybody? So really, if you just wanted the component of A parallel to B, you actually have to do some math. I'll show you really quickly what it is. It's kind of neat. This is a super valuable thing when you start doing a lot of work with vectors. But you can talk about the projection of A onto B like that. And that's actually a vector quantity. So I'll put a vector symbol over it. We know we're going to start with a dot product. But since it's a vector, I know it can't be just a dot product, because a dot product is also called a scalar product. It's only going to give me A times B times cosine theta, which has no magnitude. I mean, has no direction. So I'm going to say A dot B. Now, I really already saw that A dot B is the component of A parallel to B, which is really what I want, but it's multiplied by B. So I now need to take and divide that by B. Right? So that gives me this whole part right here is just A parallel to B, but it doesn't give me it doesn't give me a vector, right? So what I'd like to do is use the vector B to tell me what direction it's pointing. So if I multiply that by B, that would give me the right direction, but now it's off by B again. So what I'll do is I'll take and divide by another magnitude of B, and then that would make a unit vector B, meaning a vector that is exactly 1 unit long, but points parallel to B, and that's defined to be the vector divided by its magnitude. So notice the little subscript B is the one that appears all over the place in the formula, but this is an actual nice formula that can come in handy a lot of times when you're doing, say, Calc 3 stuff and other stuff in physics, statics, dynamics, that kind of thing. So that's one thing that's useful about the dot product. Another thing is the dot product can be seen to be AX I hat plus AY J hat plus AZ K hat dotted with BX I hat plus BY J hat plus BZ K hat. Well, if you just follow your rules from algebra, you're going to get AX BX I hat dot I hat, which I hat dot I hat is 1, because the magnitude of I hat's 1, times 1 again, times the cosine of 0. Well, excuse me, not theta, but 0. So you clearly get that this is just plain 1. Then you're going to get plus AX BY I hat dotted with J hat. Well, I hat dotted with J hat is going to be 1 times the cosine of 90 degrees, which is just 0. You can probably tell that AX BZ I hat dot K hat is also going to be 0. And then the next one will be 0, but then you get AY BY J hat dot J hat, which again is 1, plus 0 for the AYBZ, plus 0 for the AZBX, plus 0 for the AZBY, plus AZBZ K hat dot K hat, which again is 1. So ultimately we find that A dot B is also AX BX plus AY BY plus AZ BZ. So that's a whole other formula that you can use. So if you can find the components of a vector, you can multiply like components of the two vectors and get an equivalent of the dot product. You can compute the magnitude of each of the vectors, and then you can use that to find the angle between the two vectors, because A dot B, which can be given by AX BX plus AY BY plus AZ BZ, which is just a scalar, that's going to be the left-hand side of A dot B equals AB cosine theta. You then multiply that by the magnitude of A on the right-hand side, the magnitude of A multiplied by the magnitude of B times cosine theta. You can solve for cosine theta and then take the inverse cosine, and that would give you the angle between two vectors. So that's another thing you can do with the dot product, is you can use the two different ways to calculate the dot product, set them equal to each other, and solve for theta to find the angle between two vectors. And that's always the smaller angle. Notice here there's an angle that goes all the way around here. That's not the theta we're looking for. That's the other angle. Okay. All right. Now, one more thing that I think is cool about the dot product that I think will help you is if you imagine this. There's a vector A. Head to tail with it is a vector B. And the sum of those two vectors, of course, is C, which equals A plus B. Now, if you slide this vector A along this way, you can see that when they're head to tail, when they're tail to tail, the angle theta will be that angle. Okay. So if I do this, if I go C dot C, using the idea that A dot B is equal to A times B times the cosine of the angle between them, C dot C is just going to be C squared. A dot A is just going to be A squared, and B dot B is just going to be B squared. Does that make sense to everybody? I'm going to use those in a second. That's why I want to make sure everybody gets that. All right. Now, when I do go C dot C, that's the equivalent of saying A plus B dotted with A plus B. So that's going to be A dot A plus A dot B plus B dot A plus B dot B. Everybody follow what just happened there? Now you can see that A dot B and B dot A are essentially the same thing, but I can now use those facts that we just found to say that C squared is equal to A squared plus B squared. That takes care of that term, and that term, plus 2AB cosine theta. Well, cosine theta is kind of a pain because that's not an angle that's normally stipulated with a triangle. They don't normally give you that angle. What they normally do is say, give you the angle that is opposite a particular side. So this angle right here, for instance, might be phi. That's the angle that's opposite side C. Well, I think you can see that phi is actually the same thing as 180 degrees minus theta. Therefore, this is cosine of 180 degrees minus theta times a -1. So we can see that C squared is equal to A squared plus B squared minus 2AB times the cosine of phi, where phi is the angle opposite A. So basically, when I took trig, I never used, or I should say, when I took trig, I used the law of cosines quite frequently, but pretty much left it as soon as I got out of trig, because when I got to physics, it was always this thing where I didn't necessarily understand exactly what the angle was, whether that's supposed to be plus or minus. I'd done all this stuff, but by looking at it this way, it now makes sense why exactly you have the sides that you do have. and the angle that you do have and why the sign is negative. So once I realized I could use the dot product this way to make sense of the law of cosines, then I began to use the law of cosines again, as opposed to just always converting everything to right triangles. So that's what I'm going to say about the dot product and how useful it is. Anybody have any questions on that? Okay, so we've covered a lot of material regarding dot products. Later we'll do a cross product as well. Another name for the dot product is called the scalar product. And that should remind you, hey, whenever I do a dot product, I'm going to get just a plain number. There's no I hats or J hats or K hats in it. There's no direction to it whatsoever. There's just a positive or negative number. Okay. Now, with that being said, we next want to see another example, say, of using this work formula. Specifically, the work equals the integral of f dot dl sort of thing. So I'm going to take an example that is like the one in your book. And the example is this. We're going to have a force F given by F0 times, let's say 1 plus, let's say 1/4 x cubed over x0, excuse me, to the third power. Okay. And that's in the I hat direction. That's why I put the vector symbol over it. Let's say that F0 is actually equal to 0.00050 newtons. Let's say that X0 is equal to 0.0070 meters. And let's say we're going to take it from X1 equals 0.010 meters to X2 is equal to 0.050 meters. Okay. What I want to calculate is the work done by the force, like that. Okay. And actually, I don't like this particular value of F0 I chose. Everybody change this real quick. Let's make it a little bit easier. Let's make it 100.0 newtons. I'm just going to make the math work a little nicer, I think. So work is going to equal the integral of f dot dl. Okay. I'm actually moving from x1 to x2. So the integral is going in the positive x direction. So this is why I told you 99.9% of the path/line integrals don't matter that they're path/line integrals, because a lot of times you're just going in the positive x direction. So you're automatically doing both things in the positive x direction. So in this case, I'm going to say it's equal to the integral of F0 times 1 plus 1/4 x cubed over x0 cubed, like so. I hat dotted with dx I hat. So me choosing to call that direction dx, positive dx I hat, is one way I could use to say that I'm going in the positive x direction. But then by default, I have to automatically make the range of integration go in the positive x direction. But that's what I was going anyway. So I'm going to say x1 to x2. Okay. Now, again, I'm using this terminology. I know you're not that familiar with it, but just remember it from now on. When I say something is a vector operator, I mean, it's a linear operator, that means you can take all the stuff that's being multiplied by it and put it out in front and just let the operation go on without those parts that aren't like it. So this F0 I'm going to put out front, which isn't necessarily related to that. But what is related to what I was just saying is that I'm going to say 1 plus 1/4 x cubed over x0 cubed times dx. That's what I was talking about, putting all the stuff out in front. And then I just had I hat dot I hat. but this quantity is just 1. So that's what I meant by the linear operator. All that jump to the left came out in front of the I hat dot I hat. Now we could distribute that, but I think you see what's going to happen. I'm going to end up getting F0 times X evaluated from X1 to X2 plus I'm going to get 1 over 4 X0 cubed times 1 over 4 X to the 4th from X1 to X2. Did everybody see what happened there and why it happened? And by the way, this F0 is multiplied by all of it, so I should put that in parentheses. Okay. So I'm going to get F0, which is 100.0 newtons, times, now I'm going to say 0.050 meters minus 0.010 meters, plus, now in this case, I'm going to get 1/16, so 1 over 16 times X0 is 0.00. Oh, that just got too small. 0.0070 meters to the 3rd power is in the bottom. And notice I already took care of the 4. That's why it's 16 now. And then it's times, I'll put this in, I'll just leave another set of parentheses. It's 0.05. I'm going to leave off the units here to the 4th power minus 0.01 to the 4th power. And then close parentheses. So I've got 100.0 newtons times 0.040 meters plus, now I'm going to take 1/16. So I'll do 16. If I can get the 6 to work on my calculator. 16 times 0.007, and that's going to be raised to the 3rd power. So what I have down here in the bottom is now 0.0005488 meters cubed under 1. Now that's going to be times 0.05 to the 4th power. I'm just looking for my caret key and I can't find it to save my life. So that's going to be 625 over 10,000. So that's 0.000000625 meters to the 4th power minus the other one, which is 0.01 to the 4th power, which is 0.000, and then I got 1, 2, 3, 4, 1 meter to the 4th. So that's what the numbers worked out to be. God awful ugly right there, right? So what I'm going to do is I'm going to subtract those. You can see that you're going to get obviously a positive number when you subtract them. That's 0.00000624. And then this whole number right here becomes 1.37. So it's 100.0 newtons times 0.040 plus what I get here is 1.137. Notice this works out to be meters to the fourth over meters. So that's also meters, just like this one was meters. So 0.04, add that to it, that'd be 1.17, and then I multiply that by 100. So I get ultimately 117.7 joules. Okay, so yeah, I'm sorry I had to belabor that, but I was using a calculator that wasn't the one I normally use, so I had to go through it bit by bit. You should probably know how to do it. You're just basically doing some pretty simple arithmetic, but like I said, it made it convoluted because of the way I had to do it with my calculator, because I don't have my regular calculator. I had to use a stupid calculator on my phone. But that should be the force that you get. So that's a very typical example of how to calculate the work when a force that varies along the path is used, because you've got to account for not only how the magnitude changes, which is what was going on here, but you also had to account for how the direction of F relative to the displacement vector changes. And that's what that whole dot product worked out for. Does anybody have any questions on that? Okay. So that pretty much finishes chapter 7, but I wanted to give you a little heads up on what chapter 8 is about. Now that we've seen that work is equal to the integral of F dot dl, and we were able to find potential energy for a spring, the potential energy due to gravity. We could even do the potential energy due to Newton's law of gravity when we're dealing with distances that aren't that are bigger than the radius of the Earth. Then we have to use F equals G M1 M2 over R squared for the force instead of just mg. That mg only works when you're fairly close to the surface of the Earth. So if you actually did that, you use that to calculate a potential energy due to gravity, and you end up getting a negative Gm, where m is the mass of the Earth, over R, and that's the actual potential energy for the gravitational pull of the Earth. You can do that, and that's something you'll see in one of the examples I did. But the other thing is, now that we have these potential energies and kinetic energy, we can bring it all together and talk about something called conservation of energy, and that's what chapter 8 is about. It's conservation of energy. Now, conservation of energy isn't like, Reagan telling people to put on their, or excuse me, Jimmy Carter telling people to put on a sweater at night and leave the heat on 66 or 67 instead of 70. Conservation of energy is more like saying it's a zero-sum game. So, for instance, if we were talking about the payroll of a small company, say with 100 employees, let's say I'm one of those employees, and then there's 99 other people. If we were in a socialist world, we might want to, for instance, suggest that everybody make exactly the same because all the employees are equally valuable. And I'm not going to argue one way or the other with that. That's a whole political thing that's not really relevant to a physics class. But imagine doing that. Let's say your budget was, in fact, $100 million. That's your whole budget for payroll. You have 100 employees. So that means each employee gets $1 million per year. That's all well and good, right? Now, let's say I'm the squeaky wheel. I'm complaining. I'm like, hey, man, I'm Mr. Younger. I'm like, got this cool TCC physics and astronomy hat, and I wear these cool Tina t-shirts and kids love me. So I think I'm worth more than that. In fact, I think I want to make, let's say $9 million. Okay. So now Mr. Younger gets a salary of $9 million. What has happened? Well, what has happened is now we've got basically $91 million to cover 99 employees. So my gain was your loss. That's a zero-sum game. That's what we're talking about here. This is called a zero-sum game. Now, not all games are that way. It's not, all or nothing sort of deal. In fact, in conservation of energy, it is, but a lot of scenarios it's not. So that's what I mean by conservation of energy. So the way I picture it with this, with respect to physics, is I imagine a giant Ziploc bag, with the yellow and blue make green seal, right? So there's my little Ziploc bag, and it's perfectly airtight. But I have these semi-osmotic barriers that separate baffles. So this baffle right here might be gravitational potential. This baffle right here might be the spring potential. And this baffle right here might be the kinetic energy. Conservation of energy means that the total amount of air in that bag is going to be a constant. So if I do something like squish the kinetic energy, that means I'm going to slow the object down. That means what must happen is either the mass or the potential energy of the spring or the potential energy of gravity, or both, or just one, is going to have to go up. That's how we're going to look at conservation of energy. And in fact, I like to use a fairly different type of equation. I say work in plus potential energy initial plus kinetic energy initial is equal to work out plus potential energy final plus kinetic energy final plus E loss. So this actually allows that particular version of conservation of energy equation allows for energy losses. So this is like a bag with a hole in it because I included this term right here. And because I included this term right here and this term right here, it can actually have some pipes going into and out of the bag. If, for instance, I have a kid sitting on a sled at the top of a hill, initially he just has potential energy because he's at the top of a hill. And if he's sitting still, he doesn't even have any kinetic energy. But if I push him with a certain force, a certain distance, I can calculate a work that I put into it. And that's like putting extra air in the bag. And then when it gets down at the bottom, I could have lost some of his energy due to friction. So I would put that in the E loss category. But I could also have the kid run into a spring-loaded bumper that would allow him to slowly and gracefully come to a stop, in which case that would be work out. So that would be like a little pipe coming out. So if you left off the work out, work in, and E loss, you just have conservation of mechanical energy. And that's often what people do. They'll just say U plus K equals a constant. But by using this version, you'll have a little bit more freedom, and you can even account for when it says something random, like if you assume 20% of the total energy was lost due to friction, then you can just automatically calculate the total energy initial, multiply it by 0.2, and stick it in that E loss slot, and you're done. The only thing is you got to make sure you don't count things twice or skip things to be counted. So that's it. That's all I wanted to do with regards to getting you started on Chapter 8. The Chapter 8 homework is available, but it's not due until not this coming Sunday, but the Sunday after. That's when we're going to really cover Chapter 8. So I might even be able to do 8, 9, and 10 next week. I'm going to go ahead and let you guys go. I know we're 25 minutes early, but I really can't do much more with Chapter 8 in the time allotted. And I think y'all deserve a little break to prepare for your test, which is going to be on Monday. So go take your practice test, go take your practice midterm. Both of those, remember, you need to take both of those because I'm going to average the highest grades on all those, and that's going to be counted as extra credit at the end of the semester. But other than that, you're free to go. Let me stop sharing my screen. So everybody's free to go. If you have any questions, I'll wait for the last person to leave.
I don't have a question, but I won't be here on the 6th, which I believe is a test day. Would you like me to email that to you? And then could you give me any direction as to what I need to do to make that up if you want me?
Is this Courtney speaking?
Yes, this is.
Okay. It depends. If I end up making that a face-to-face test, which is currently the situation, then either I'd need you to take it before you left or when you get back, and I'm just setting that up like in a testing center or something.
Okay.
Okay. If it's an online test, you can take it while you're gone if you want. But if you are somewhere where your internet's bad or you don't have access to stuff, then that's not a problem. You can just take it when you get back. Just remind me when you get back and just before you leave.
Sounds good. I'll be in Florida, so if it is take home, I'll be able to.
Florida has no internet. No, they actually have plenty of internet. But if you're on vacation, you might not want to take a test. So I'll work with you.
Sounds good. Thank you so much.
You're welcome. See you, Courtney.
Yeah.
Anybody else? Nora, Samuel, Caston?
Nothing yet. I was looking through something because I thought I had a question earlier, but I think I got distracted and forgot to ask it.
Yeah, I got a little ADD myself, so sometimes I just lose my concentration.
That's how it is. That's how it is.
Well, everybody's got a touch of it. It's not necessarily a disease until it becomes a problem. Well, if you think of it, send me an email or whatever.
All right, sounds good. For the midterm,
Mhm.
that's a separate test from our third test, right?
It's actually the same thing. If I made a test 3, that would have been online, and then a midterm, that would have been a face-to-face. But I just decided to make it both one. So we might at the end of the semester have 5 or 6 tests instead of just the number that I had suggested. Some will be online, some will be face-to-face.
Okay, so this one you're planning to either make it face-to-face and have it be our midterm, which will be cumulative for all the units that we've covered?
Yes, this one will be Monday,
Oh, okay.
and it will be 100% cumulative 1 through 6, and it will be face-to-face. I already made that decision.
Okay, gotcha. Thank you.
No problem. See you, Nora.
See ya.
Okay, so I won't be able to attend the class on Monday or Wednesday because I'll be out of the state.
Okay.
So I heard you talking to Courtney about having that like done at the testing center.